Hello students, in this video I would like to discuss about specification of tokens in lexical analysis. Here in this slide I am going to discuss about strings and languages. These things you already studied in formal languages and automata theory. So first one is symbol. Symbol is the smallest building block which can be any alphabet, letter or any picture. Symbols are generally known as characters. Typical example of symbols are letters, digits and punctuations. Alphabet, it is denoted by sigma. Alphabets are set of symbols which are always finite. And for example, while we are considering English language, we are only considering about that 26 uppercase A to Z symbol and 26 lowercase A to Z symbols. So alphabets are set of symbols which are always finite. The set 0, 1 is the binary alphabet. So binary alphabet is an example where the set contains two symbols 0 and 1. Next point, a string over an alphabet is a finite sequence of symbols drawn from that alphabet. We all know what is a string. For example, in English language we call it as words. So a group of characters from that particular alphabet is considered as string. We already studied sigma stands for alphabet. Sigma star means it's a set of all possible strings. So for example, in binary alphabet, sigma star means set of all binary numbers. Then language. A language is a set of strings chosen from some sigma star, or we can say a language is a subset of sigma star. I will try to explain language with the help of a simple example. Consider the binary alphabet. I am going to define a language where the rule is the strings which begin with 0 and ends with 1 will be considered as a language. Actually, it is a subset of sigma star. A language can be formed over sigma, can be finite or infinite. So in our example, it is an infinite set, because we can generate infinite number of strings which starts with 0 and ends with 1. For a finite example, if we consider keywords alone in a C language, it is only a finite set. That means some 32 keywords are there. So that can be considered as a finite language. The length of a string S, usually written as absolute of S, is the number of occurrences of symbol in S. Length of string, we all know, number of symbols in a particular string. The empty string denoted by epsilon is a string of length 0. So this epsilon symbol you already studied in flat. Abstract languages like null, the empty set, or epsilon, the set containing only the empty string, are languages under this definition. So null language means that language didn't contain any string. That set is empty. And that epsilon symbol means a string of length 0. Next is operations on languages. In lexical analysis, the most important operations on languages are union, concatenation and closure. First one is union of L and M. If a string S is a member of L or M, we can say S is an element of the language L union M. Next is concatenation of L and M. LM equal to ST such that S is in L and T is in M. So some set of strings are there in L and some set of strings are there in M. Concatenation means the first string is from set L and second string is from M. Clean closure, that means 0 or more occurrence of a string. Positive closure means 1 or more occurrence of a string. This is an example for operations on languages. Let L be a set of letters A, B up to Z and small letter A, B up to Z, and D be a set of digits 0, 1 up to 9. So here I have two languages, L and D. L contains some 56 strings and D contains 10 strings. It is worth noticing that this A, B, Z, all elements in this set are considered string, not as symbols, because L is a language which contains 56 strings. From this language you can't say cat is a member of this language L. This language L contains only the characters of single length which is of English alphabet, and D is of digits. So we may think L and D in two especially equivalent ways. One way is that L and D are respectively the alphabets of uppercase and lowercase letters and of digits. The second way is that L and D are languages. All of those strings happen to be of length 1. Here are some other languages that can be constructed from L and D using the operators. So using the operators we can construct new languages. L union D is a set of letters and digits, strictly speaking, a language with 62 strings of length 1. That means 52 plus 10, each of which string is either one letter or one digit. Similarly, LD is a set of 520 strings of length 2, each consisting of one letter followed by one digit. LD will contain strings of length 2, and the first string will be from L and second string will be from D. In L we have 52 strings and D we have 10 strings. So 52 into 10 is 520 strings. L4 is the set of all 4 digit strings. L star is a set of strings of letters including epsilon in the MD string. So L star means set of all possible strings that we can generate from L. So that is another language. Similarly, L4 is another language which contain a different set of strings. Also L star contain a MD string epsilon. Then L union D star. Here also we are concatenating L and L union D star. Is a set of all strings and letters and digits beginning with a letter. Fifth language is something very similar to identifiers. We already studied identifiers always start with a letter or underscore followed by any combination of letter and digit. D plus is a set of all strings of one or more digits. That is another language. So D plus contain all possible digits we can generate from 0 to 9. So always remember L and D are languages. L union D is another set of language. LD is another set of language. Similarly, L raised to 4, L star, L union D star and D plus are another set of languages. Next is regular expression. A regular expression is described as a sequence of pattern that defines a string. So regular expression can be defined as another way of expressing language. In the previous slide, we see one method of expressing languages using the operator. So another way of expressing the strings in the language is regular expressions. For example, here we have two symbols A and B. The regular expression A or B denotes the language A comma B. Here A or B is a regular expression. That means the strings may be either A or B. So another one A or B, again A or B denotes AA, AB, BA, BB. That is another language of all strings of length 2 or the alphabet sigma. Another expression for the same language is AA or AB or BA or BB. These two are equivalent. Then A star denotes the language consisting of all strings of zeros or more A's, that is epsilon A, AA, any number of A's. A or B star denotes the set of all strings consisting of 0 or more instances of A or B, that is all strings of A's and B's. For example, epsilon A, B, AA, AB, BA, BB, AA. That means any combination of A and B including epsilon. Another regular expression for the same language is A star, B star, the whole star. Here one thing you have to notice is, here this is A and B are considered as symbols. In the earlier example, that A to Z in both small caps and larger caps are considered as strings. Next one is A or A star B denotes the language A, B, AB, AAB, AAB, etc. That is the string A and all strings consisting of 0 or more A's and ending in B. So this language contains set of strings which is either a single A or 0 or more A's and ending in B. So regular expression is another way of representing language. There is no need to denote all the strings in a set. Just describes as a sequence of pattern. So we already studied what is pattern. Now you may connect regular expression and pattern what we studied in the compiler design. For example, For identifiers, we already know identifiers will start with a character or underscore followed by digits. So now you can imagine how we can represent that identifiers in the form of regular expression. So if you remember one thing what you have studied in the previous semesters, we can represent or we can draw finite automata for regular expressions also. So here we are using finite automata for identifying the valid lexemes. So anyway, we will study those things in detail later. So next one is grammar. It is a formal rule which is used to generate all possible patterns of strings in a given language. So in the previous slide we studied some more languages. There we define some rules. A or B the whole star. That means that rules saying that it is a combination of all A's and B's. So here grammar G can be defined by 4 tuples. G equal to NTPS. N stands for non-terminals. T stands for terminal symbols. P is a set of production rules. S is the starting symbol which is used to derive the string. We can derive the string by repeatedly replacing a non-terminal by the right hand side of the production until all non-terminal have been replaced by terminal symbols. The same definition of grammar you already studied in the previous semester. So I will try to explain grammar with the help of some example. So in this example it is about C identifiers. C identifiers are strings of letters, digits and underscore. Here is a regular definition for the language of C identifiers. We can conventionally use italics for the symbols defined in the regular definitions. Here we have 3 productions. Letter underscore may be any alphabetic letter plus that underscore symbol. So letter underscore is a non-terminal. Digit is a non-terminal which can have terminals in the form 0 to 9. So identifiers can be defined as it will be start by letter underscore. That means first character or first symbol may either be a alphabet from A to Z or an underscore followed by anything. Any combination of letter and digits that is denoted by letter underscore or digit star. The regular expression within the bracket saying anything. Letter underscore is before that, that means letter or underscore followed by anything. That is a valid identifier in C. So this is a grammar which defines C identifier. So next example is a grammar to define unsigned numbers. So now finite automata and lexical analysis. This token can be recognized by finite automata. A finite automation is a simple idealized machine used to recognize pattern with an input taken from some character set. Here we are discussing about deterministic finite automata. This finite automata, its type, deterministic finite automata, non-deterministic finite automata you already studied in the previous semester. And it is worth noticing that both DFA and NFA has equivalent power. So this definition you already studied. Q means set of all states. In this diagram we have states from 0 to 8. Sigma means a set of input symbols. Here input symbols are less than, equal to, greater than, equal to. These are the valid input symbols. Q means initial state. Here 0 is the initial state. F is the set of final state. Here we have 2, 3, 4, 5, 7, 8 as final state. Set of final state. And transition function. Here transition function is represented with the help of a transition diagram. So this finite automata is actually to identify relational operators. So here I saw a less than. Suppose I say one more equal to also, then it will return less than or equal to. Suppose I first saw a less than, then again I saw a greater than, then it will consider as a not equal to. Never compare it with this C operator. This is not equal to operator used in some other language. Similarly, if equal to alone is recognized, it will return EQ, equivalent operator. Or here also never compare it with C language. This equal to means a relation operator which check whether two quantities are same. Again, if a character is greater than, and if it is recognizing any other character, it will be considered as greater than alone. If you are saying equal to also, it will be considered as greater than or equal to. So now I think you got an idea to identify lexemes or to find the varied lexeme in compilers we are using finite automata. This is all I want to share in this video. Thank you.